Asteroid impacts have always held a certain fascination for us. While not an everyday occurrence, the prospect of an asteroid striking Earth captures the imagination and serves as a gripping theme for disaster movies. The reason? Such an event is believed to have caused the mass extinction that wiped out 76% of all species on our planet 66 million years ago. This raises an intriguing question: was that a one-time catastrophe, or could it happen again? And if a massive asteroid were on a collision course with Earth, would our current technology suffice to prevent disaster and ensure survival? I'm Alex McColgan, and you're watching Astrum. Today, we delve into the story of the DART mission, humanity's pioneering attempt to alter the trajectory of an asteroid and shield our world from future existential threats. Major impact events have played a pivotal role in shaping Earth's history. In the nascent solar system, one of the most significant collisions may have led to the formation of the Moon, when a planet-sized body known as Theia collided with the young Earth. As time passed, these collisions might have also brought water to our oceans. Since then, asteroids have potentially been responsible for several mass extinctions. One of the most famous impact events created the Chicxulub crater, which is thought to have triggered the extinction of the dinosaurs 66 million years ago. There's an inverse relationship between the size of an impacting object and the frequency of such events. Small objects collide with Earth frequently, while large object impacts are rare. As the solar system ages, large asteroid impacts become less common. When asteroids collide with other bodies, they either break into smaller fragments or become part of larger entities like planets. Earth gains an estimated 15,000 tons per year from meteors entering its atmosphere. Impacts occur more often than you might think, but most are hardly noticeable. Meteors, or shooting stars, are minuscule, ranging from sand grains to stones only a few centimeters in size. They burn up upon entry into Earth's atmosphere. How many do you think hit Earth's atmosphere daily? The answer might surprise you: 25 million. And the largest one likely on any given day? About 40 centimeters across. Annually, the largest meteor measures around 4 meters, and every century, an object at least 20 meters across impacts the Earth. Meteorites, the objects that survive Earth's atmosphere and reach the surface, are larger than typical shooting stars. Usually, what's left upon impact is about the size of a brick. These objects create bright trails in the sky, known as fireballs. Approximately every 2,000 years, a meteor around 100 meters in size hits the Earth, causing significant damage not only from the impact but also from the associated airburst. Then there are objects large enough to threaten entire civilizations, over 10 kilometers in size, which appear once every several million years. The odds of experiencing such an event in our lifetime are nearly zero. The good news is that larger objects are easier to detect, and scientists believe they have identified all nearby asteroids above 10 kilometers with a high degree of certainty. However, smaller, less detectable meteors pose a localized threat. In 2013, around 1,500 people were injured and the Chelyabinsk meteor exploded over Russia, damaging about 7,200 buildings across 6 cities. Fortunately, there were no fatalities, but imagine if such a disaster occurred in a densely populated area. The results would be catastrophic. This underscores the importance of detecting and preventing potential impacts before they happen. One way to do this is by locating and tracking space objects that could pose a threat. We've become faster and more efficient at this task, discovering over 20,000 potentially dangerous asteroids in the last 2 decades alone, with about 30 new discoveries each week. While most have harmless orbits, what if we identified an asteroid on a collision course with Earth? This question led NASA to explore solutions through the DART mission, the Double Asteroid Redirection Test. The DART mission was a collaborative effort between NASA and Johns Hopkins Applied Physics Laboratory, with international partners from Italy, Japan, and the European Space Agency. Its objective? To attempt to redirect an asteroid's trajectory by deliberately colliding a spacecraft with it. Numerous ideas had been proposed for preventing an asteroid collision before DART. If we had sufficient warning and the asteroid was small enough, we could send a spacecraft to accompany it, acting as a gravity tractor. Over time, the spacecraft's gravitational influence might nudge the asteroid's orbit slightly, steering it away from Earth. Though it might sound far-fetched, in 2015, NASA published an article asserting that this method was feasible. A more popularized notion involves detonating a nuke near the asteroid. Asteroids aren't densely packed, so blowing them into tiny pieces seems straightforward. However, despite its depiction in films like Armageddon, this approach might not work as effectively in reality. The asteroid's momentum could largely remain intact, even as it fractures, potentially turning a metaphorical bullet aimed at Earth into a deadly shotgun spray. Another idea involved deploying reflective mirrors to an asteroid. It's well documented that comets outgas when they heat up as they near the Sun, gaining propulsion away from it. Spacecraft with mirrors could travel to an asteroid and reflect sunlight onto its surface, causing it to outgas and propel itself away from Earth's path. The creators of DART decided on a more straightforward solution, one that we had previously executed successfully with a comet, directly impacting the asteroid. The goal wasn't to destroy it but to nudge it just enough to alter its course. After settling on this kinetic approach, mission planners had to select a suitable test asteroid to target. They chose Dimorphos, first discovered in 2003. It's a small moon in a binary system, orbiting the larger Didymos, which was identified in 1996 by Arizona's Spacewatch project. Dimorphos spans just 160 meters, significantly smaller than the 780-meter Didymos. It orbits its larger counterpart every 11.9 hours, maintaining a distance of roughly 1 kilometer. The system orbits the Sun every 2.1 Earth years, coming close to Earth in October 2022, at a distance of 10.6 million kilometers, the closest since its discovery in 2003, making it the ideal candidate for this mission. This proximity made Dimorphos accessible, yet it was distant enough not to pose a collision threat to Earth, even if knocked off its trajectory. With the target set, NASA needed to build the perfect spacecraft for the deflection mission. Compared to other spacecraft, DART was relatively simple. About the size of a refrigerator, it weighed a mere 610 kilograms, dwarfed by Dimorphos's estimated 5 billion kilograms. DART carried a single payload, an aperture camera named Draco, Didymos reconnaissance and asteroid camera for optical navigation, along with sensors and an autonomous navigation system. It was paired with a small secondary spacecraft called LICA-Cube, essentially making it a binary spacecraft visiting a binary system. Built by the Italian Space Agency, LICA-Cube was a small CubeSat with its own autonomous navigation system, designed to separate from DART 15 days before impact. LICA-Cube's mission was to document the impact and its aftermath using two optical cameras named Luke and LEIA, a nod to Star Wars fans. Weighing just 14 kilograms and measuring around 30 centimeters in length, LICA-Cube would fly by the asteroid system using its autonomous navigation capabilities. The DART spacecraft was designed to operate autonomously. Given the communication delay due to the vast distance from Earth, DART needed to locate the moonlet, pinpoint an ideal impact site, and aim appropriately. This is where DART's Smart Nav system proved invaluable. This autonomous optical navigation system could identify and differentiate between the two celestial bodies, lock onto its target, and guide the spacecraft toward it. Remarkably, all this would occur within just an hour before impact. After launching on November 23, 2021, aboard a SpaceX Falcon 9 rocket, DART spent the next 10 months in transit. 4 hours before the anticipated impact, from a distance of 90,000 kilometers, DART's internal navigation system took control. 90 minutes prior to impact, the Smart Nav system set the spacecraft on its final trajectory. When DART was 24,000 kilometers away, Dimorphos appeared on camera, occupying a mere 1.4 pixels. This is one of Draco's last images, capturing both Dimorphos and its parent asteroid together in the frame. As DART approached its target at a speed of 22,000 km per hour, Dimorphos and the potential impact site came into striking view. In an image taken just 3 seconds before impact, you can see how Dimorphos is essentially a loose pile of rubble, remnants from the solar system's formation. This remarkable photograph stands as DART's final fully transmitted image, taken from a distance of 12 kilometers, a mere 2 seconds before impact. For reference, the scale is about 3 centimeters per pixel. And here is DART's very last, partially transmitted image. The transmission was interrupted by DART's planned, shall we say, disassembly. As strange as it sounds, this incomplete image is one of my favorites. Its unfinished nature seems to capture the drama and intensity of the moment, freezing in time the breathtaking instant when DART completed its 17.5 million kilometer journey in the blink of an eye. To the very end, DART executed its mission with incredible precision, a testament to the ingenuity of NASA's team. Here is the entire sequence, sped up and presented as a time-lapse. The video corresponds to the final 5.5 minutes of DART's approach. As you'll notice, some images appear blurred due to DART's ion thrusters, which caused vibrations that affected the spacecraft and its camera. This sequence is astounding, considering the speed involved. It managed to impact such a tiny object. I'm amazed that some of these images are in focus at all. Imagine how quickly the camera had to adjust to the fast-approaching target. Now, I'm sure you're eager to know whether the impact was successful. To ease your suspense, the answer is, yes. In fact, the early results have exceeded expectations. Before DART's kinetic impact, NASA defined success as altering Dimorphos's orbital period by at least 73 seconds. Yet, based on current data, DART shortened Dimorphos's orbit by a full 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. Even with a margin of error of plus or minus 2 minutes, this is 25 times NASA's benchmark, a truly remarkable achievement. The impact released 19 gigajoules of energy, equivalent to nearly 5 tons of TNT, and carved a crater up to 150 meters wide on the asteroid's surface, impressive considering the Moon was only 160 meters to begin with. It was sufficient to alter the shape of Dimorphos' orbit and the asteroid itself. Originally, Dimorphos had a circular orbit around Didymos, but post-impact, this path became more elongated. The orbital time also continued to drift over subsequent weeks, eventually stabilizing at 11 hours, 22 minutes, and 3 seconds. Regarding its shape, before the impact, Dimorphos resembled an oblate spheroid, a slightly squashed sphere. Afterward, it transformed into a triaxial ellipsoid, akin to an elongated watermelon. It's fascinating to consider the forces required for such a transformation. It also underscores the fluffy nature of asteroids like Dimorphos. Loosely held together by gravity, they can significantly change shape if hit with the right force. But there's no need for concern. Even with significant variability, scientists are confident that Didymos's orbit won't shift enough to ever cross paths with Earth. However, if an Earth-bound asteroid existed, a small nudge, if administered far enough in advance, could deflect it off a collision course. So, why did the impact shorten Dimorphos's orbit? According to orbital mechanics, the crash pushed Dimorphos closer to Didymos, speeding up its orbit. Scientists confirmed this through observations from optical telescopes on Earth, including the Southern Astrophysical Research Telescope in Chile. SOAR also captured some of the best images of the encounter, including a breathtaking photograph of a 10,000-kilometer debris trail 2 days post-impact, giving it a comet-like appearance. Since Didymos is a two-asteroid system, its brightness varies as Dimorphos moves in and out of its parent asteroid's shadow. By tracking the light curve, scientists can calculate Dimorphos's orbital speed. Radar data from observatories in California and West Virginia further supported these findings. DART and Earth-based telescopes weren't the only ones capturing the event. The closest images of the crash were taken by LICIACube, and they are phenomenal. As mentioned earlier, LICIACube separated from DART 2 weeks prior to impact to conduct its own flyby using autonomous navigation systems. 2 minutes and 45 seconds after DART's impact, LICIACube flew past Dimorphos, photographing the impact site with its evolving plumes and ejecta. One action-packed image shows Dimorphos post-impact, with Didymos overexposed in the foreground. Notice the vast plumes of material emanating from Dimorphos, some spiraling like vine tendrils, indicating directional changes in the plume's growth. This phenomenon might be due to the asteroid's composition, as impact tests on fine sediment mixed with coarser debris sometimes yield similar patterns. This is a more distant image captured by LICIACube, showing Dimorphos on the rightmost side, almost obscured by the massive clouds of material splashed up by the impact. Hubble and the Webb telescope also joined in capturing the aftermath of DART's impact. Here, you can see a stunning series of images from Hubble, portraying the plumes growing in size and number. Notice how some plumes appear as rays emanating from the asteroid, and intriguingly, some of these rays are curved. The reason for this is currently unknown to NASA. While Hubble observed the impact in the visible spectrum, the Webb telescope captured it in the infrared spectrum. This is quite impressive, given that Dimorphos was moving 3 times faster than Webb was designed to track. The time-lapse begins just before impact and continues for 5 hours afterward. Notice the sudden flare of light, coinciding with the material released upon impact. I love how the Webb images give a clear sense of the spiraling plumes coming from the asteroid. In the coming weeks and months, scientists will continue to analyze the data from DART's impact. However, the more comprehensive investigation will be conducted in the future by Hera, a follow-up mission by the European Space Agency. Scheduled to launch on October 7, 2024, Hera will arrive at the Didymos system by 2026. Equipped with a sophisticated payload of instruments, including cameras, a spectrometer, and an altimeter, Hera will meticulously document the size, shape, and composition of the crater left by DART's impact. Most excitingly, Hera will explore Dimorphos's internal and subsurface structures. This will not only deepen our understanding of the binary Didymos system but also provide insights into how near-Earth objects, NEO, physical properties affect momentum transfer. Additionally, it will shed light on how kinetic energy is transferred to a NEO and its ejected materials, offering valuable guidance for enhancing deflection technologies in the future. When combined with NASA's missions like NEO Surveyor, which aims to discover at least 90% of asteroids 140 meters or larger, it seems humanity has, for the first time, actively reduced the risk of a catastrophic impact like the one that likely wiped out the dinosaurs. Although NASA already tracks most NEOs, some, like dark comets, are harder to detect because they don't reflect much visible light. NEO Surveyor, proposed to launch in 2028, will scan the solar system for such objects by taking infrared readings, identifying hard-to-spot asteroids by detecting the heat they emit when warmed by the sun. It will also be able to detect asteroids approaching Earth from our blind spots, like those coming directly from the sun's direction, which ground-based telescopes might miss due to glare. With even the hardest-to-see NEOs being identified, the technology proven by DART will serve as a protective shield for our planet. So, there you have it, a comprehensive look at the DART mission. We've only begun to scratch the surface of deflection technologies, yet this mission suggests that the future of planetary defense has embarked on a bold and promising journey. Do you think this mission was worthwhile? Will we need to employ this technology within our lifetimes? Share your thoughts in the comments. If you recall, a few months ago, I shared a video about how the support from our Patreon astronaut crew allows for greater creative freedom and stability in creating these videos. I was truly touched by your response and wanted to express my gratitude to everyone who joined. For the past few months, I've been working on a special project, astronaut pins. They've just arrived, and I couldn't be happier with them. I'll be sending one to every paid member, so if you'd like one, you can still join and support the channel's mission. We'll ship them before November 29th, so be sure to become a member before then to get your hands on this limited edition pin. As always, thank you for making this channel possible. Thanks for watching, and a big thank you to our Patreon astronauts. It's becoming a thriving community, and I've loved reading all your messages and comments. If you'd like to join, you can visit the link in the description to become an awesome note and bring the channel more stability than the algorithm. Once you join, you'll enjoy ad-free videos, see your name in the credits, and submit questions to our team. Again, a heartfelt thank you from me and the entire Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.